Hello guys, am I audible? That's fantastic. So let us start the session. My screen is visible to you guys, right? Okay, so welcome to IIT Gate classes. So today we will be discussing about Gate Aerospace 2020 program. 1 second. Okay, so today we will be discussing about jet propulsion part of the Gate Aerospace 2020 paper. So myself Akshay. So in 2020, so we had around 11 marks out of core jet propulsion, out of which like 3 were 1 mark question and 4 were 2 marks questions. So here like we can see much of the theory driven questions. So it is a very interesting paper, I can say. So let us jump into the problem. So the first question is, the ratio of exit stagnation pressure to inlet stagnation pressure across the rotating impeller of a centrifugal compressor operating with a closed exit is. Okay, there are so many terms which makes it confusing, but we really don't have to worry too much on the given statements here, because like we know compressor is a device which is used to raise the pressure, right? So there is an energy transfer from the machine to the fluid or the system, right? So which raises the pressure. So the obvious answer for this particular question is going to be option C. Option C, right? So this would be a correct choice. The next one, in an aircraft engine thermodynamic cycle analysis, perfectly expanded flow in the nozzle means that the static pressure in the flow at the nozzle exit is equal to. So this is again a straightforward question. Say like I have a convergent nozzle. Okay, so the upstream of this one is connected to the turbine exit plane. So I have some pressure P naught and temperature T naught, say stagnation condition at the upstream of the nozzle, and it expands in the nozzle or in the converging duct to a exit plane pressure PE. So this is purely governed by the nozzle geometry, how it has to expand from P naught to PE, right? So if we assume it to be isentropic flow, so I can easily relate it to be P naught by PE is equal to 1 plus gamma minus 1 by 2 times ME square to the power of gamma by gamma minus 1. So purely governed by the geometry. But so they are saying it perfectly expanded flow. What do we mean by perfectly expanded flow? When the exit plane pressure, which is also equal to, so the aircraft is operating in certain altitude or some atmospheric value. So say PA and TA. So this is the atmospheric condition of the air surrounded by the engine. So now if it is expanded perfectly to the atmosphere, that means PE should be equal to PA, right? Note here, so from here we can easily guess the answer, which of this is correct. The stagnation pressure at the engine inlet, the stagnation pressure at the nozzle exit, the ambient pressure at the nozzle exit, the static pressure at the nozzle inlet. So we can easily get. So PE and PA, they are the static pressures at the nozzle exit plane. So it has to be balanced, right? So, but now here is the catch. So since this question is being asked, so there are a few things we can actually discuss here. So one part is nozzle is going to expand the fluid to the exit pressure condition, not to the exit temperature condition. Though TA might be the condition of the surrounding fluid in terms of temperature, but the exit plane temperature need not be equal to the exit ambient temperature. So it can be different. T can be higher than TA or less than TA. It really doesn't matter. TE is again purely governed by the nozzle geometry. So it is governed by the energy equation. So if I have a streamline, I have to choose which is going from this turbine exit condition to nozzle exit plane. So I call it is 0.1 and 0.2. So if I apply the energy equation, for a steady adiabatic flow, so it comes out to be H1 plus V1 square divided by 2Cp equal to H2 plus V2 square divided by 2Cp, where V2 is my exit plane velocity. So H2 can be written as so if I assume it's calorically perfect, so Cpt2 plus V2 square divided by 2Cp. And if I assume very low subsonic value at the entry of the nozzle, so this becomes my stagnation condition. So that is Tp T naught, right? So from here, the exit plane temperature is actually defined. So I can write T naught by T2 or Te for this condition to be equal to 1 plus gamma minus 1 by 2 times Me square, right? So this is purely governed by the nozzle geometry, not and the physics. Okay, so it need not be expanding to the exit ambient condition at the nozzle exit plane, right? So this is a very important point. So we only equate the pressure because these are pressure driven flows. The pressure gradient is what driving the flow, but the velocity and the Mach number at the exit plane of the nozzle is set by the temperature difference. Okay, so this is a very interesting physics to catch here. Yes, Ashish, you have any question? You raised your hand. You can speak up, no problem. Okay, sure. So let us move on to the next question. Air enters the rotor of an axial compressor stage with no pre-whirl, that means C theta is equal to 0, and exit the rotor with the whirl velocity C theta is equal to 150 meter per second. The velocity of the rotor vanes U is 200 meter per second. Assuming Cp is 1005 joules per kg Kelvin, the stagnation temperature rise across the rotor is. So it's a very interesting question again. So 1 mark question, remember. So what's the condition they are given in this problem? The air enters the rotor stage. That's an axial compressor stage, right? So let us try to draw the stage velocity triangle first. Okay, so usually I'll be having a velocity triangle for the axial compressor. Say I have a rotor which is rotating in this direction with the velocity u, right? So u, and the condition is given in the question such that which enters the stage with no pre-whirl. That what does it says? It means the absolute velocity vector is also equal to axial velocity vector. So that means C1 at the entry is equal to CA. So that's what they are actually saying. And we know the vector relation, that is C is equal to U plus W. So if I use that one, so the rotor is receiving the fluid at an angle to the axial component of velocity, that is a relative velocity beta 1, right? So this is my entry velocity triangle. If you are able to draw this triangle correctly, then your half of the job is done. So then as it is, it leaves the rotor with a relative velocity component W2. And again, if we assume the blade velocity to remain same, U, and the absolute velocity vector at the exit of the stage is going to be again given by the vector relation C is equal to U plus W. So this is going to be C2. And again, we are assuming axial component of velocity is to remain constant. That's the assumption we are going to take. So with respect to CA, absolute velocity vector is making alpha 2. The relative velocity vector is making beta 2. Right. So now our velocity triangle is with us. So now we can easily proceed for the problem. So in the question, they are also given the blade velocity, the magnitude 200 meter per second, and they are also given the values of tangential component of absolute velocity, that is CT1, which is equal to 0, and CT2, which is equal to 150 meter per second. So this is given in the question. So what is CT2? CT2 is this one, the tangential component of absolute velocity vector, CT2. This is given in the problem. So they are asking you to calculate the temperature rise in this stage. So I have at the entry T01, and at the exit of the stage I have T02. So the actual exit of the stage comes after the stator, but the stator we know it is energy transformation. So for an adiabatic flow assumption, T02 should be equal to T03. So we can just if we calculate T02 minus T01, that is the rise in temperature in the stage. That's enough, right? So how can we relate it? So again, getting our help from the thermodynamics. So that is steady flow energy equation or first law applied to the flow process. So work done can be written as change in internal energy, that is nothing but which can be shown to be U times CT2 minus CT1, right? So now you see work done can be represented as Cp times T02 minus T01 in a stage equal to U times CT2. Why only CT2? Because CT1 is 0. So now everything is with you. Just calculate T02 minus T01 equal to U CT2 divided by Cp. So 200, 150, 1005. So that should give you the temperature difference in this stage to be 29.9 Kelvin. So go back, round off to one decimal place and just write 29.9 Kelvin. Everybody clear? Yes. So now we will move on to the next question. Okay. Again related to axial compressor. Axial compressor is designed to operate at a rotor speed of 15,000 rpm and an inlet stagnation temperature of 300 Kelvin. During compressor testing, the inlet stagnation temperature of the compressor measured was 280 Kelvin. What should be the rotor speed for the compressor to develop the same performance characteristics during this test as in the design condition? Very interesting question. Any of the formulas you might have studied in your propulsion might not going to help you over here. It's more of a qualitative approach than the quantitative approach. And how we are actually trying to analyze this problem is by dimensional analysis. Because now we have the same compressor which is being tested under different conditions, but we want to get the similar performance characteristic. That means we want to match the dynamics of the flow which the compressor is encountering under two different test conditions. So consider the scenario to be two different tests, or at two different places you are testing the same compressor. That is how the question is framed, right? So now if I want to compare the exact performance characteristics, we know that any fluid mechanics problem can be addressed either through integral approach or through a differential approach. The third one is through a dimensional analysis. So this comes under the dimensional analysis category, right? So here, what we have to do is we have to match geometric similarities, kinematic similarities, and dynamic similarities. And the first two options, the geometric similarities and kinematic similarities, are already matched because of the problem statement. The only thing we have to match here is the dynamic similarity. So to do that one, we have to match the dimensionless numbers, which are much more important to the given problem, right? So if I get the compressor as a whole, so I can have very important parameters, the variables like P01, P02, P01, T02, the mass flow rate. So I will write it to be RT01 and RT02 so that my dimension will reduce, and mass flow rate, and maybe the geometric parameter, the diameter. So if I do this one, so I should be able to get the important non-dimensional numbers, that is P02 by P01, similarly T02 by T01, and the non-dimensional mass flow rate for this one. So because we are using the same gas in the both the condition and same geometry in this both the condition, I can just non-dimensionalize with T01. So I am actually neglecting other variables which makes it non-dimensional. It is fine. So n divided by root T01. So or root T0, whatever. Okay, so it depends on the reference temperature we are taking. Fine. So now, out of this one, we are only interested in this parameter which sets the rotational speed, right, for a given inlet temperature, right? So in both the cases, only thing we are varying here is the temperature, the stagnation temperature at the inlet. So if I want to compare with that one, so now if I want to compare, it's much more easier. So all I have to match is this one, n1 by root T01 should be equal to n2 divided by root T02. So in the problem which is given, n1 is given, T01 is given, T02 is given. They are asking what should be the n2 to match the same performance characteristics. So just put the numbers now. So N1 is 15,000. T01 is 300 Kelvin. Equal to N2 is unknown divided by square root of 280 Kelvin. So if you put that one, you should be able to get N2 to be equal to 14,491 RPM. So if you look at the option now, so option B is correct. But here is a catch. Like now we analyze this problem in a systematic way, so we should be able to get the correct answer. If you take a guess, what happens? If you take a guess, see, first of all, this is 2-mark question. And second of all, there is a negative mark for the wrong answer. So if you just take a guess, what if I do this like this? N1 into root T01, which is equal to N2 into root T02. So and calculate N2. What you are going to end up with? You will end up with an answer that is 15,526. That is again wrong answer. If in case you do like this, T01 is equal to N2 divided by T02. Again, you are going to end up with an answer that is option A, which is again wrong. Or if you do like this, N1 T01 is equal to N2 T02. Again, you are going to get a wrong answer that is 16. That is one of the option. So in these scenarios, you will end up with an answer which is given as an option, but it's wrong. So this is where like guessing the answer is going to be cost you. So make sure if you know this answer correctly, then put it or else skip it, because this is 2-mark question and there is a negative marks because it's MCQ. Okay. So now we will move on to the next question. That is question number 5 for this session. It's again 2-mark question. The design flight Mach number of an ideal ramjet is 2.8. The stagnation temperature of the air at the exit of the combustor is 2400 Kelvin. Assuming a specific heat ratio of 1.4 and gas constant of 287 joules per kg Kelvin, the velocity of the air at the exit of the engine is. So it's again a straightforward question. We are given a ramjet engine. Let us try to draw the control volume for the given option. Given question. So I have a ramjet engine. Right. So I have an incoming condition. That is my free stream condition with Mi in that Mach number, and it is exiting with Me, exit Mach number. Corresponding velocity at the nozzle exit plane is going to be Cj or Ce, whatever you want to call. It's fine. This is what we have to calculate, and the given condition are such that it is having incoming Mach number of 2.8, right? And they are also given. So if I have a nozzle within the control volume, let's draw it clearly. So it makes right. Because it's a ramjet engine, we will be having converging diverging nozzle. So this is my nozzle exit plane. This is my nozzle entry plane. And we know ramjet is having no moving parts. So that means no turbine and no compressor as a mechanical components. So after the combustion, so whatever you have, the temperature, that is going to be your inlet condition for the nozzle, T03. So that is given in the problem. So I'm just stating this is state 1 state 2, state 3, and state 4 is the exit plane. Okay, so T03 is given in the problem. So T03 is given in the problem as 2400 Kelvin, and the gas constants are given such that gamma is 1.4 and R is 287 joules per kg Kelvin. So it is also given in the problem. So the main important thing we have to note here, it is an ideal ramjet. What do we mean by ideal ramjet? Ideal ramjet means that the inlet Mach number and exit Mach numbers are same. That's it. Okay. So many a times people will make a confusion out of ideal ramjet and ideal cycles. They are different. Ideal ramjet does not necessarily mean that it is following the ideal Brayton cycle. No, it can still have adiabatic efficiencies associated with intake, adiabatic efficiencies associated with the nozzle. Ideal ramjet only confirms you that the inlet Mach number and exit Mach numbers are same. That's it. Okay, so this is the distinction we have to make clear. Okay, so now if it is given like that, so then we can easily calculate the exit plane condition because we know the exit Mach number, that is same as inlet Mach number. So I know what is exit Mach number. So that is nothing but 2.8. So if I use that condition and again consider any streamline which is passing in the nozzle. So if I apply the energy equation between the entry to the exit plane, so that means T0 equal to TE plus Cj square divided by 2Cp. I'm just applying the adiabatic energy equation, right? Steady flow energy equation again. So now I can easily write it for Cj. It is going to be square root of 2Cp times T0 minus Te. And how I can calculate Te? So that is again I can calculate using the help of energy equation only, because I know the Mach number. So I can replace this equivalently with the help of the Mach number, that is T0 divided by Te is equal to 1 plus Cj square divided by 2Cp times Te. So that is equal to 1 plus Cj square divided by Cp can be written as gamma R divided by gamma minus 1 times Te, and gamma R Te is nothing but speed of sound squared. So that gives me gamma minus 1 by 2 times Cj square divided by A square, that is going to be Mach number, right? So from here I can calculate what is Te because T0 is given in the problem. So I can calculate Te. So or else T0 by Te can be equally represented with this relation. So I can write, if I take T0 common, so that becomes 1 minus Te divided by T0, that is going to be 1 divided by 1 plus gamma minus 1 by 2 times Me square, right? So now you put all the numbers which is with you. Cp can be again calculated using gamma R divided by gamma minus 1. So you should be able to get the value of Cp. You replace that one, you can get the number, that is Cj equal to 1715.8 meter per second. So this problem I approached from a very basic understanding of the flow physics. That means like I'm applying the laws of thermodynamics as well as fluid mechanics as long as it's applicable here. So we can also approach in other way, that is like slightly shorter way, but again that way is coming from this um, basic understanding of our fluid dynamics and thermodynamics. So we are applying it in the right way. So that is, I know what is ME, right? So ME is already known. So that is 2.8. So what is CJ? CJ can be written in terms of ME times square root of gamma or TE. So that is nothing but because the Mach number is defined such that it's the speed of the fluid to the local speed of sound. So if I just multiply the speed of sound, so I should be able to get. So this one you calculate first. T naught by TE is equal to 1 plus gamma minus 1 by 2 times ME square. So from here you calculate what is TE and put it over here to get the CJ. So this is also the right approach you can do. Okay, so in both the ways you should be able to get the answer as 1715 point round off to 1 decimal places. So I am just rounding off to 1 decimal place, 8 meter per second. So everybody clear? Okay. So let us move on to the next question. Operating conditions of an aircraft engine combustor are as follows. The rate of total enthalpy of air entering the combustor is 28.94 megajoules per second. The rate of total enthalpy of air leaving the combustor is 115.42 megajoules per second. Mass flow rate of air is 32 kgs per second. Air to fuel mass ratio is 15.6. Lower heating value of the fuel is 46 megajoules per kg. The efficiency of the combustor is. It's a very interesting question. Again, you see here, the question, the type looks very familiar, but the units not. The moment when you realize the given units are in different form, you should be able to answer it, or else you will keep on looping along the formula what you have studied and you will never end up with the correct answer because units are different here. So we usually saw that the unit of enthalpy will be like in joules per kg or joules, right? So but here it is given joules per second. It is a different unit than what we conventionally use in our classes, right? So that is where this problem is very interesting. Okay, so now let us try to see this problem very carefully from a control volume approach. So I'm just drawing a control volume for the combustion chamber. So what do we have here? I have the incoming condition. So at the inlet of the controls volume, and I have an exit condition, and I have a mass of the fuel which is being added with the calorific value denoted by QCV, right, of the fuel. So now here I have the rate of enthalpy, that is nothing but H dot not 2. So the dot represents with respect to time, right, rate, and I have the rate at which enthalpy is exiting the combustion chamber is denoted by H naught 3. So now if I want to balance the energy equation, so that's again applying the first law of thermodynamics with no work transfer involved within the controls, within the system. So I can easily show that the change in enthalpy is going to result in the heat addition. So that means H dot naught 3 should be equal to enthalpy at which the mass is entering the system plus the energy what you are adding, which is converted into a form of heat, right? So now what is this H naught 3? That is mass flow rate of the what is coming in? Mass flow rate of the air. What is going out? Mass flow rate of the gas, because mass flow rate of the gas is nothing but mass flow rate of air plus mass flow rate of fuel given by continuity. So mass flow rate of the gas times Cp of gas times T03 should be equal to mass flow rate of air times Cp of air times T02 plus. So I have certain energy associated with the amount of fuel, that is mass flow rate of fuel times the heating value of the fuel. That is the energy, the maximum energy you can extract from the fuel, but out of which only this much percentage is only to be used as the energy addition. So this gives me the efficiency of the combustion. Okay. Now look at the unit carefully. What is mass flow rate of the gas, which has the unit of, so let me just use different color, makes easier. So mass flow rate of gas has kgs per second, Cp has joules per kg Kelvin, temperature has the unit of Kelvin, so that cancels out both the side. kg cancels out both the side. I am left with joules per second. So this side also same thing, joules per second. So what is the unit of this one? Efficiency has no unit. It has kg per second times this is joules per kg, right? So now kg get cancels. I am again left with joules per second. So unit wise they are matching, so no problem. Now look at the problem. They are already given in this form, joules per second, and this one is given in joules per kg. But when I multiply with the mass flow rate of the fuel, so that again comes into joules per second. So now unit wise they are already balanced, right? So now I can easily use this equation or the given numbers as it is. So that means my units are not going to be missed out. So what is given? The rate of enthalpy at which the flow is entering, that is 28.94 megajoules, 94 megajoules per second, and rate at which enthalpy is exiting from the combustion chamber, that is 115.42 megajoules per second, plus efficiency, that is unknown, the mass flow rate, that is so now I have to calculate mass flow rate of the fuel, which is not given, but air to fuel ratio is given. Air to fuel ratio is given to you, that is 15.6. So if I have the air to fuel ratio and mass flow rate of the air is also given to you, that is 32 kgs per second. So I can easily calculate mass flow rate of the fuel should be equal to mass flow rate of the air divided by air to fuel ratio, that is 15.6. So you can replace here 32 divided by 15.6 kgs per second times the lower heating value, that's the calorific value of the fuel, that is given to you 46 megajoules. 46 megajoules per kg. So that again gives me in megajoules per second, the total unit. So now in all the condition, I can cancel out this mega, that is 10 to the power of 6, right? So I don't have to put in numbers there. So now my energy balance is much more simpler, that is 115.42 minus 28.94 into 15.6 divided by 32 whole divided by 46 should be equal to efficiency, right? So this is the balance. So now if you calculate you should able to get eta B is 0.9165. So now look at the question carefully, how you are supposed to answer. You want to you should answer in percentage and rounding after 2 decimal places. So in percentage wise, it is going to be 91.65 rounding off to second decimal place. Percentage. Clear? Okay. So again, this question is relatively straightforward, but they are not given in a conventional way how you are used to practice in the classes. So they are given the map to you, that is Molnier diagram or TS diagram, and from here you have to pick the information to calculate. So the calculation is going to be very straightforward the moment when you understand the TS diagram. So here it's across the axial turbine stage. So that means the flow is expanding from T01 to P01 to P02. So I have an expansion ratio P01 to P02. So how do we define the efficiency? So they are asking you to calculate the isentropic efficiency of the turbine stage. Okay, so for the gas which has the gas constant or specific heat ratio 1.33. So let us just put over here gamma is 1.33. Okay. So now let us understand this diagram a little bit carefully. If it has expanded ideally to the same pressure P02, you would have got the temperature, say T02 dash. So you would have converted much more energy into useful form. So why? Because this is a straight indicator. So the H02 minus H01 is going to be work done by the turbine, right? So that means for calorically perfect gas, T02 minus T01 is equal to work done by the turbine. So if you have or the turbine is able to do the work purely in isentropic manner, that means on a constant entropy line, you would have experienced the ideal expansion. So the work transfer is going to be Cp times T02 dash minus T01. So instead of that one, you are getting only T02 minus T01. This is less than the ideal work. So if I want to define the efficiency now, so efficiency of the turbine due to an expansion is going to be work done in the turbine in an ideal way, in an actual way, divided by work done in the turbine in an ideal way, right? So that means a CP can get cancelled, assuming it's a calorically perfect gas. So that is nothing but T02 minus T01 divided by T02 dash minus T01. Or you can write in the other way, because T01 is higher than T02. So we will be consistent, divided by T01 minus T02 dash. Both are same. So it's just the difference we are interested in. But this is much more conventional way, right? So now the numerator part is straightforward. It is already given in the problem. But the denominator T02 dash is not given. Instead, what we have is the pressure values. So for that, what I am going to do, I am going to take T01 common. So that makes 1 minus T02 dash divided by T01. Now look at the TS diagram very carefully. T02 dash and T01 both falls on the same entropy line. So that is S1 is equal to constant, let us see. So that is a constant entropy line. That means the change in entropy between T02 dash and T01 is 0. So I can use isentropic relation. That means as long as it is following the same entropy line, so my S2 minus S1 is going to be 0. So I can use the isentropic relation here. So this one is going to be T01 minus T02 divided by T01 times 1 minus. So I can equally replace that one with the pressure ratio P02 and P01. Note here, this pressure ratio is actual pressure ratio. So I can write P02 divided by P01 to the power of gamma minus 1 by gamma. So now everything is known to us. So just put the numbers T01 and T02. So T01 is 1050, T02 is 823 divided by 1050 times 1 minus what is P02? P02 is 2.5, P01 is 7.8 divided by 7.8 to the power of gamma is 1.33. So that is going to be 0.33 divided by 1.33. Right? So efficiency of the expansion or the turbine should come around 80.8789. So again, look back the question, how it is asked in percentage and rounding up to 2 decimal places. So that is going to be 87.89 percentage. So clear? Yes. So that ends our discussion for the 2020 gate paper. So if you have any question, you can pitch in now, or else we can wind up the session. Thank you. Okay, then we will wind the session over here. Thank you for attending.